What stops a hacker from just guessing Alice's 6-digit login code? And why does a number that expires on its own turn out to be more secure than most passwords ever created? Alice wants to log into her bank. Passwords can be stolen, guessed, or reused across dozens of sites. A one-time code fixes all three problems at once, because it works exactly once and then disappears forever. The login API is the stateless brain of the operation. Any server in the fleet can handle any request, and it coordinates every other piece you are about to see. Here is the full picture. A fast in-memory store holds a scrambled version of the code for a short window. An SMS gateway pushes the real digits to Alice's phone. A rate limiter guards the front door. And the user database creates her session at the very end. Alice taps "Send me a code." Her phone sends a request to the login API, just her phone number, nothing else. The API generates a random 6-digit number, that is 1 million possible combinations, then immediately runs it through a one-way scrambling function so the raw digits never touch permanent storage. The scrambled value, not the code itself, gets written to the OTP store alongside an auto-expiring timer. When the timer runs out, the record vanishes on its own. No cleanup job required. At the same time, the plaintext code travels to the SMS gateway. The gateway converts that number into a text message and fires it toward Alice's carrier. A few seconds later, the code lands in Alice's messages. She has a short window. The exact length varies by service, anywhere from 1 minute to 10, to type it in before it disappears. Alice types the 6 digits and taps verify. The login API now has one question to answer. Is this the right code, and is it still inside its window? Before touching the OTP store, the API checks the rate limiter. If Alice's number has already collected too many wrong attempts, say 5, the code is locked and she must request a brand new one. The API scrambles what Alice typed and looks up that results in the OTP store. If the scrambled values match and the record has not expired yet, it is a valid login. The moment the code is verified, it is deleted from the store permanently. Even if someone intercepts the text a moment later, that code is already gone. It cannot be used a second time. The API writes a new session record to the user database, generating a long random token that Alice's browser will attach to every future request it makes. That token flows back to Alice's device. She's now logged in, no password was ever sent, stored, or needed at any point in this process. Now let us look at why this design resists attack even when parts of it fail. The first layer is the expiry window. A code that has already disappeared cannot be guessed because the attacker is racing a clock they are already losing. The second layer is the attempt cap. Each phone number gets at most a handful of tries before the system walks them out. 1 million possible combinations mean nothing if you only get 5 guesses. The third layer is scrambled storage. If an attacker dumps the entire OTP store, they see garbled values. Reversing the scramble to recover the original 6 digits is computationally useless in the seconds the code is still active. Put the numbers together. 1 million combinations, a 5-guess limit, and a short expiry window means the odds of a random guess succeeding are roughly 1 in 200,000 per window, and that ignores rate limiting on fresh code requests entirely. Rate limiting on the request side closes the last gap. Even if an attacker scripts fresh code requests to the same number over and over, the system throttles them before they can gather any useful timing information. One important trade-off: the OTP store must be a shared, low-latency store that every server in the fleet can reach. With multiple stateless API servers, a code written by one server must be found by a completely different server during verification. A local in-memory map breaks this completely. Request a code, store only the scrambled version, race the clock, lock on failure. 6 digits turns out to be a remarkably well-engineered security layer when the system around it is built right.